Sorry, we were having technical difficulties, but welcome to Book Club. This is, today is April 26th, and we are talking about, we're reading the book 7 Languages in 7 Weeks, and today we're talking about Prolog, and we have a special guest from Bendyworks, Nick.
An expert in Prolog.
Yes, yeah. our resident expert. He's gonna show us how it's done. Anyway, without further ado, let's go ahead and dive right into the first part. Just to kind of continue on, you know, the author makes, you know, comparisons of what the programming language would remind him of, and this one was the character Raymond from the movie Rain Man, and which I thought was interesting. So, Nick, do you want to add something to that?
Not really, unless you want to just get started with.
Let's dive right in there, man. Let's do it.
All right. So let's see here. We got a nice long introduction about Prolog. Okay. So Prolog is set up as a system where you define facts and rules, and then you can ask questions of the system and have inferences made based on the facts and rules that you provided. All the facts and rules need to be defined in a .pl file, then that gets loaded into the interpreter, and then you can ask questions from it. The facts and rules go into a knowledge base. Basically, it's got a database behind the back end that it then does queries against. And Prolog, in general, works as a depth-first search through all of the rules and facts that you provided to try to find any combination of facts that will make your query evaluate to true. So, let's see here. He definitely talks about the fact that sometimes you think that something should work in Prolog, but it won't. Just because sometimes you have to tinker around with it until you get used to the tail recursion system. There are certainly ways to write valid Prolog programs that run exceptionally long. And then if you can optimize the tail recursion on there, you can make a lot of performance and, improvements on that. So, some basics. Anything that is lowercase is a symbol. So that would be similar to like a symbol in Ruby. You could think of it as a string, but it's more or less just defined as an object. Anything with an uppercase is a variable, and it's something that can be assigned values to make sure that the query that you asked evaluates to true. So in the first example here, we've got just a couple of definitions of facts. Wallace likes cheese, Gromit likes cheese, and Wendelin likes sheep. When you read Prolog statements, they're typically the first parameter, the name of the fact, and then the second parameter. So, like I said, Wendelin likes, let me get my mouse in the right place, Wendelin likes sheep.
So it's like list, but they don't put the parenthesis around the function as well.
Kind of, yes. Except you don't really necessarily define nested functions as often. So anyway, these first ones are facts. They're defined by just the predicate, the values, and then a period at the end saying that the statement is over. This down here is a rule. Friend is a rule. And basically what this is saying is that a friend is defined between x and y, which are variables. Those will be assigned values to make the statement come true. X and y are friends if x is not equal to y. So this backslash plus means it's a negation operator, and that x does not equal y. Comma, saying that there's more rules. X likes some unknown z, and y also likes some unknown z. So two people are friends if they like the same thing, whatever that thing may be, and they're not the same. So Wallace and Wallace can't be friends. When you put this through the system, you can start asking questions against it. You load the file by just typing in bracket, quote, the name of your .pl file, quote, bracket, period, to say that your statement is over. Then you can start querying it. So the question, does Wallace like sheep? No, Wallace doesn't. Does Gromit like cheese? Yes, Gromit does like cheese. So this is the very basics of how facts can be interpreted as either true or false based on what you defined in your .pl file. So then we get to asking questions about whether or not two people are actually friends. As you can see, Wallace and Wallace are not friends because the first definition in the rule set is that X and Y cannot be the same. But Gromit and Wallace are friends because they both like cheese. And also Wallace and Gromit are friends because the order doesn't matter as long as X and Y both like the same Z.
Do you want to run this on the terminal?
Yeah, I can
So I'm working.
pull this up here on the terminal.
And by the way, we had some issues installing it, installing it on his computer actually, because he tried to install it from scratch. So what we did is we removed every instance of it everywhere. And the easiest way to install it is to use brew install GNU Prolog, GNU-Prolog. And that will get you up and running with that, with the G Prolog.
Yeah, I was having problems installing it from source from the Prolog site. So as you can see, our standard queries of whether or not people are friends work just fine. So like I said, that's a very, very simple example. What it does when it starts looking through this is it looks for values for X and Y based on this likes clause in here. So first it'll try every value of X and Y that it can. It'll assign, for example, Wendelin. And it'll find out that Wendelin is equal to Wendelin, so that doesn't work. Then it'll try Wendelin Gromit, finds out that they don't like the same things. Then it'll try Wendelin Wallace, finds out they don't like the same things. And then it'll finally try Gromit and Wallace. Gromit and Gromit, they're the same, and then Gromit and Wallace finally result in two likes that can be determined to be the same. So let's go to a more complex example where we're actually defining kind of a nested relationship where different foods have different types. So for example, the food type of Velveeta is cheese, food type of Ritz is crackers, Spam is meat, sausage is meat, etc. And then for flavors, we define the flavor and then the food type. So sweet for dessert, savory for meat, savory for cheese, and sweet for soda. Now to ask a question of what food flavor, well, first to ask what food has what flavor, we define this rule that the food flavor of XY is the food type of XZ, the flavor of YZ. So if you look here, food type has the first parameter being Velveeta, for example, the second parameter being cheese, and then flavor is savory and cheese. So when you combine these two, those are both assigned to Z, and then it tries to find X's and Y's that match those. So if we take a look at this in Prolog, we'll load our food types.
It's thinking, the declarative languages don't have any, what we're used to in Ruby of, step by step, this is what happens, this is what you do, There's no, basically code, you're just writing stuff that you say, these are the rules and these are the questions, so figure it out. So.
Okay, so we're going to ask the question, does the food Spam have the flavor savory? And it first checks, it assigns Spam to X, savory to Y. Then it checks, of all the food types that are listed, if Spam is one of them, Z gets assigned whatever its food type is. Same with the flavor. Savory is selected, so it'll first try meat and then it'll try cheese. And at meat, it evaluated to true, so it just gives us the answer. But because there's another one that it could check, which is the savory cheese, it lets us query it again. It lets us see if there are any other ones that could be possible values. In this case, if we hit semicolon, which queries it again, it says no, there are no other ones. Now this is where we can start asking true questions. For example, food, flavor, what has savory? Put a period at the end to finish the query, and it's going to start spitting out values for what that makes this statement true. So Velveeta is a possibility, Spam is a possibility, sausage is a possibility. Then there's nothing else that fits under the flavor of savory. We can also do a what for Velveeta. We'll see that it's savory, and that's the only food flavor that's associated with it. So basically it's doing a very simple depth first search right now, just to determine an extremely simple relationship. Once again, if it's not certain that whether there are any other values, you have to hit semicolon. It'll return no if it finds no other values. If it's certain that there are no other values, it'll just spit out the answer and then return yes. So it's one thing to keep an eye out for. Let's see here. So we've got some more queries in here. Okay, then we get into map coloring. Do you want to add anything to any of this?
Well, I was just thinking, do we want to move on to the recursion stuff?
Sure,
So
we can skip ahead a little bit.
Skip the map.
Yeah, map coloring is a fairly simple system that just defines the differences between various parameters and then makes sure that all states have different values for red, green, and blue.
I thought that example was pretty interesting because it's the first time it didn't feel like a toy example. You were solving a real problem.
That's true.
Right.
And so the basis of this is just that you have to define every single combination of colors that would be considered different. And then for this coloring, Alabama, Mississippi, Georgia, Tennessee, and Florida, all of them have uppercase values. So that means that they're variables. They can be assigned to anything. So if you state that the coloring says that, for example, Florida and Georgia can't have the same, have to be different. Florida and Alabama have to be different. Alabama, Mississippi, Alabama, Georgia. All those need to be different from each other. But for example, there's no rule that says that Tennessee has to be different than Florida or Mississippi has to be different than Florida. So you specify all the relations in here that different has to evaluate to true for, and it will start assigning various colors to these values, doing a depth first search until it finds a combination that works. The very first thing it'll try is making them all red. And then it'll try changing, let's see, so Georgia and Tennessee would be false. So it would replace Tennessee with blue. Then it finds out that Georgia and Tennessee are fine, but Georgia and Florida are not. And it keeps going until it finds a pattern that works. Once you get your answer out, you can query it again and it'll spit out other combinations of colors that work. So yeah, that is a little bit less trivial of an example. But where Prolog really comes into its own is when you start using recursion on it. And let me get, see if I can find an example for that. There's a little bit of talk on here on unification. That's basically this, the idea of a statement being true. if it can find values for all variables and unify them, then it'll return the answer and it knows that it's found a correct solution. If it cannot unify everything, then it just returns no, and you have to redo your constraints because something's wrong. So let's see here, we'll skip the Wizard of Oz example here. And let's see. Then we get into an interesting discussion about some real world uses from the 80s that were involving training dolphins, and the fact that there are only 4 research dolphins that they had access to, but they had quite a few research studies that they needed to do. Quite a few staff members who had different roles or capabilities for these studies, different availability, stuff like that. And so for on a weekly basis, they had to figure out the most efficient way to get as many research projects done as possible with the staff that they had. So they would just define all the facts about each of the employees, each of the dolphins, and each of the projects, and ask Prolog to spit out an answer. The problem with it is that Prolog is kind of an all or nothing system. It will either find a solution eventually and give it to you, or run for a while and say no. And then you know that there's no possible way to meet all the criteria that you've specified, and you have to loosen your constraints here. So we'll move on past that. And now we're on to day 2. Okay, so now we're talking recursion. And Prolog uses a Taylor recursion system similar to many Lisps and whatnot, where you can talk about the head of an array and then the tail of the array. You can also do a recursion based on facts. So this first example, we've got the definition of father being the father of the second parameter is the first parameter. So Zeb is the father of John Boy Sr. John Boy Sr. is the father of John Boy Jr. So that's easy enough to figure out. Then it gets interesting when we start talking about ancestors. Because an ancestor, the easiest kind of ancestor is just if you're the father of someone else, then you're their ancestor. So that's this first rule here. Now Prolog will actually let you define many rules with the same signature, and it will try them in order. So if you ask a question of this system, first it'll try to assign x and y, see if father x and y evaluates to true. If it does, then you've got your answer and it returns. Otherwise, it'll try the second definition of ancestor. The second definition of ancestor has a recursive call to itself. Basically what it's stating is that x is the ancestor of y if x is the father of z, and z is an ancestor of y. So in the simple case up here, you can say Zeb is the father of John Boy Sr. John Boy Sr. is an ancestor of John Boy Jr. because we defined ancestor to be father. If there were more descendants listed here, it would just continue to recurse over the various values until it found a path through fathers from your x to your y. So that's the basics of recursion based on rule definition. And I think we're going to get to, yep, lists and tuples.
This is, I had some stuff that I had highlighted on it, but if you want to start on it.
No.
Let me get to it.
Okay, so unification, similar to what was stated up above, unification is all about making both sides of the equation equal. When you're dealing with tuples, which are in parens, they're equal if and only if they're exactly the same. So 1, 2, 3 is equal to 1, 2, 3. 1, 2, 3 is not equal to 1, 2, 3, 4. Similarly, 1, 2, 3 is not equal to 3, 2, 1. It's an ordered list of values, and they have to be absolutely identical. So you see a simple case of unification is just to ask the question for A, B, and C, unified against 1, 2, and 3, what are the values of A, B, and C? It says they're 1, 2, and 3. You can do it the opposite direction, works the exact same way. You can even mix variables on either side, and it'll come up with the answers. So then lists are done with braces, and lists are typically used for recursive processing. In this case, we're not to recursion yet, but it's just showing that it unifies in the same way. The list 1, 2, 3 is unified with the list 1, 2, 3. 1, 2, 3 with x, y, z returns x is 1, y is 2, and z is 3. And similarly, you can use a variable multiple times as long as it can unify. So in this case, x can be 2 in both cases, and z can be 3, so it unifies.
But if you did 1, 2, 3, x, x?
Yep, if you do 1, 2, 3, x, x, z, it can't, because there's no value of x that's both equal to 1 and 2. Alright. So,
Go ahead.
so now we're getting into actual tail recursion. And anyone who's familiar with a Lisp, this is the same as car and coulter. When you talk about a list and you put in elements and then a pipe, everything, the variable after the pipe is considered the rest of the array.
It's also the same as head and tail in Haskell.
Alright. So in this case, if we do the list A, B, and C and we ask for the head, it's going to be A. The tail is going to be the array B, C.
Would this be like star args in Ruby? So,
Sort of.
well, you can just pop the first element of the array and then say comma.
Yeah, this is more specific, I would say.
Yeah.
Sort of like destructuring an enclosure.
Yes. So, and this gives it almost a functional element in defining your rules. So, let's see here. So, an empty set will not unify with head tail because there is no head. Tail can be an empty array, but head has to be defined as something. So the array or the list of A does unify with head tail. Tail is just empty. Let's see here. You can also use other combinations in your array definitions. You can nest lists inside each other. So in this case, we've got A. The tail is going to be defined as the list head tail, and so then head is going to be B in here, and tail is going to be the array of C. You can also put in underscores. Underscores are a special type of variable that doesn't actually get bound to anything in particular. It can just be any value. You're just not testing against it. So, looking at recursion against lists, one of the important things to remember is on any recursive or tail recursion system, you have to define what your termination point is. So in this case, they're defining the rule count, which says that the count of an empty array is 0. The count can also be defined as the variable count for an array with head and tail, which is defined as the count of the tail count against tail. So that recurses down the tail until it gets to an empty array, which is 0. And then it says that count is tail count plus 1. So then it'll start propagating back up and keep adding 1 until it gets back to the entire array and return the value. Same with sum. You're essentially memoizing the sum into a variable called sum. And actually you're storing it into total, and then sum is being returned. So then average can be defined as the sum of a list, the count of a list, which binds the variables sum and count, and then the average is defined as sum divided by count. Is the operator for actually assigning a value to a variable. Equals is only for testing for equality. So, if we do a count of a single element array, we'll get a 1. Yeah, it's pretty simple math stuff there. There's some deeper discussion of exactly how it recurses through these. In this case, sum of what is going to be 6, and it's actually going to say the sum of this array is going to be equal to 1 plus the sum of the tail, which is going to be equal to 2 plus the sum of the tail, which is going to be equal to 3. So that it'll just recurse back up and you'll get your answer 6. So that's pretty simple. Let's see here. Alright, so we've got a couple of useful methods for applying to lists. For example, append will take 2 lists and put them together. You can also ask questions in append, just like you can ask questions in any other rule. So in this case, if you append tiny to bubbles, what do you get? And it returns that it's tiny bubbles. If you append dessert topping to something, it should result in dessert topping, comma, floor wax. That something has to be the array of floor wax. So it infers all these values based on what it knows about appending things. Also, if you ask it, what can you append to what to get this order 3 list? Well, the first thing that it can do is it can append an empty array to the list that you're looking for. It can append apples to oranges and bananas, apples and oranges to bananas, or apples, oranges, and bananas to nothing. So there's 4 solutions to that that all work. The first one that's tried is assigning these to 2. If you say that that's not correct, then it'll try the next possible option, which is just oranges and bananas, and then apple assigned to 1. So.
And why does it return no there?
Down here?
Yeah.
It returns no because at this point it's not sure whether there are any more solutions. So when you ask it for another solution, it'll say no, there weren't any.
Okay. Gotcha.
If it knew at this point that this was the end and that there were going to be no more solutions, it wouldn't ask you anything. It would just spit out yes, that it had found the end of its processing and that there weren't going to be anything else. So, all right, so concatenate. Let's see here. Okay, so this is basically how you would write append if the Prolog that you're using doesn't have append. And basically, appending is done through recursion. Appending nothing to a list returns just that list. Appending something with an empty list to a list returns that something and that other list. So yeah, that just returns the exact same thing as append did. Let's see here. Any questions from anyone?
Do you think do you want to cover the queens?
Yeah, we can get to the
your
queens part.
queen implementation. The
Sure.
8 queens.
I was going to see if there was anything else. Okay, so what we learned in day 2. So
Yeah.
that's basically the end of day 2. It teaches a bunch of the basics of how recursion works. So as a kind of a fun problem, this is a very traditional problem for Prolog, solving the 8 queens problem. For anyone who doesn't know, the 8 queens problem is taking a chessboard and 8 queens. Can you place the 8 queens on the chessboard in such a way that no 2 queens are attacking each other? So this is a very recursive problem. There are a lot of solutions out there, and there's actually a solution later in this book that I don't think is the same as this one, but I haven't read it yet. So we're just going to go through how you would actually solve this problem from the very beginning. So the first thing that you would want to define is what is a queen position. A queen has to be somewhere on the board. It's going to be an x and y value that's between 1 and 8 for both x and y. So with this queen position definition, we can start asking questions about what are possible queen positions. We'll load our queens file, we compile, and then we say queen position of S. And then it'll start showing us possible queen positions.
Prolog is .pl.
Yeah.
Yes. Yes.
Hold on,
It
read
thinks
that as
it's-
Perl.
Yeah.
I know.
Wait,
Which
he
one's
changed
older?
it?
How old is
Yeah.
Prolog? I don't even know.
Oh, it's
Prolog's old.
It's
That's what I
older.
thought.
Yeah.
I was curious. It's in a new book.
So in this case, it'll start looking for values of x and y that's fulfill these parameters, and first thing that works is 1 and 1. So if we ask it again, it's going to try y, because it always does the second half first. So it's going to return 1 and 2. And if we keep running it, it'll hit 1 and 8. It'll try 1 and 9. 1 and 9 doesn't work, so it goes to 2 and 1. And you can just keep running through all these until you get to the end. And it does all 64 possible places for a queen. Second part of the problem is that we need to define a solution format. The solution format, we can cheat a little bit by knowing that since no two queens can be in the same x column, we can just define our solution format as being a list of queen positions where the x is 1, the y is something, x is 2, y is something, x is 3, y is something, and so on. And then you can try asking that a question.
Do you mind clearing, communicating that so it
Okay.
can be shown better up?
Okay, so you can do solution format of S, and in this case it's just returning nothing. It doesn't know what it is that you want, because there are no actual specifications in here. This is just a fact. So we need to start defining some more rules about what can actually go in here. So the next thing that we want to define is, what does it mean for one position to be attacking another position? There's an operator in here that's not talked about in the book that's equals/equals. Equals/equals means that the left-hand side is not numerically equal to the right-hand side. So this can be a little confusing.
This also equals colon equals,
Yes.
which means that it is numerically equal.
Right.
So you can say 2 plus 2 equals colon equals 4, and that's true.
Right. So,
Or,
so
yeah, there you go.
yeah, so in this case we're going to say 2 plus 4 is equal to 6. No, it's not. 2 plus 4 is equal to 4 plus 2. Oh, no, it's not. 2 plus 4 is only equal to 2 plus 4 because they're structurally the same. If you want to, if you want a numerical equality, you can do a
Colon.
equals colon equals.
Now,
and
what if you
yes.
instead of 6 you use x? Does it find 6 for you?
No.
This language sucks.
But if you define, and I'd have to do it in another file, if you define the rule 2 plus 6 x is defined as 2 plus 6 equals colon equals x, then you can ask it a question and it'll return a value for x that is valid. So
And that's how you do addition. Great.
yes. So if you do the slash, it'll do the numerical operator and it'll say that no, they're not equal, but 7 is not equal to 2 plus 4. So over here what we're saying is that given the two position, resize that. Given the two positions x1, y1 and x2, y2, these positions are not attacking each other if y1 and y2 are not equal, so they're not in the same y row. And also, the value of y1 minus y2, which is the row offset, is not equal to the x1 minus x2, which would be the column offset. That means it's in the same diagonal in one direction. And you also have to say that it's not equal to x2 minus x1, so that it's not equal to the offset in the other direction. So this is basically saying not in the same column, or not in the same row, not on one diagonal, not on the other diagonal. So then we can ask the question over here, not position attacking, and we'll give it 1, 3, 1, 4. Actually, we'll do 2, 3. And it says that no, those positions are attacking because they're in the same column. If we do 1 and 3 and 2 and 4, they're on the same diagonal. If we do 1 and 3 and 2 and 7, those positions are not attacking each other. So we've got a definition of what positions are or are not attacking each other. So now we start getting into the recursive part, which is where the problem solving actually happens. So the first thing that you want to do is test whether or not the first element in a list is attacking any other element in the rest of the list. So we first define our terminating condition saying that anything is not going to be, anything cannot attack an empty array. There's nothing to attack. So that'll be our terminating condition. Then our definition of the no attack test for a non-trivial example would be grab the value of first, and then grab the rest of the array, grab the value of second, and then the tail of it. So the first thing we do is we call no attack test against first and rest, and that'll recurse all the way down until it gets to the very end of the array, and this returns true. Then it'll start trying to find values at that point for first and second that are both queen positions, and that first is not attacking second. Once it finds that, it starts moving back up the list, tries to find another first that isn't attacking second and the rest of the list, and it'll keep going until it determines that no pieces in that list are attacking each other. So then the other thing that we have to do is we have to iterate over the list to make sure that, for example, the 7th element is not attacking the 8th element. The 6th element is not attacking the 7th or the 8th. The 5th element is not attacking the 6th, 7th, or 8th. So we define this no attack list rule that says that an empty array is not attacking, that there's no attacking happening in an empty array. That's our termination. And then we say, given a standard list, split out the first and the rest, iterate down it until you get to the very end, and then start checking this no attack test to make sure that the value of first is not attacking anything else in the list. So at that point, that's all the logic that's needed to define the solution to the 8 queens problem. So then we just need to define the actual question, which we're going to say is 8 queens solution, which will bind to S, is valid if S is in the solution format. So all of these arrays or all these lists evaluate to true, and that that no members in S are attacking each other. So at that point, we can just run 8 queens, ask it for solution, whatever we want to call that, and it returns a valid solution for the 8 queens problem. You can then start going through and asking for other solutions, and it'll continue to give different versions of the solution set. Some of them will be mirrored, some of them will be rotated.
So there's you didn't do the A, B, C, D, E, F, G, H, right? So that coordinate. So it's like 1 through 8, 1 through 8, and so 1, 6.
Correct.
2,
And
4.
the reason for that is because we have this math over here that says that we have to be able to subtract the y values.
Right.
So,
That's why this is a lot simpler than what he has in the book.
okay.
What he has is like huge.
We could assign those letters to numerical values, right?
Yeah, you could write a rule that would then just translate this and output based on the other values.
That's pretty neat.
So, and you can also hit A and it'll just print out all of them. And then you can also go in and start doing some interesting things in here to make the process faster. If you'll notice, if we run this again and quit, oh, if I can quit correctly, it's taking 4 milliseconds to run that query. Now we know that, for example, some of these can be put in a certain quadrant and it won't affect the actual result because there are many solutions to this problem. So if we defined another rule in here that said, actually we'll make this part of the same rule. We'll say that, let's say column 6 should have a very specific y, and that y should be in the list 1, 2, 3, and 4. So it's never going to try 5, 6, 7, and 8. The reason that we're putting it near the end is because that's where the recursion happens, that's where it's trying new values. So you don't want it to try many values of 6 and then switch to changing what 5 is, try another whole bunch of values for 6, and so on. So we say that 6 should be between 1 and 4, and that's the end of our rule. And we'll reload the system. Now if we ask for the solution, it only takes 2 milliseconds to run. So there are a lot of ways to improve the efficiency of the tail recursion. A lot of them aren't necessarily apparent. Another way to improve the efficiency is to always make sure that you're calling the recursive call first. If we took this and put it at the end here, all these rules are still the same. It's still asking the same question. But if we reload it and try to get a solution. Oh, actually that one was
Makes it dramatically faster.
Is it this one? Yeah, this is the one that. Let's see.
Yours has 3 minutes.
Okay, so then if we run this, it takes 62 milliseconds. And that's because it's first testing all possible values for the entire array and then iterating through it. So it's actually testing 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6, 1, which is completely not valid. And then it's doing the recursion. So this is where some of the frustration comes in with Prolog, is that the order of what you do is very important. And yeah, you just kind of have to think about the way that it's recursing and how the variables are being unified. So anyway.
Yeah, I think we can wrap up Prolog with its strengths, being, natural language processing. It's been used for games. There's mentions of the semantic web. That's what it says. The semantic web is an attempt to attach meaning to the services and information on the web, making it easier to satisfy requests. And then talks about the RDF.
Does it talk about the cloud?
I don't want to talk about the cloud. It's been a thorn in my flesh lately. Artificial intelligence of obviously
Logic.
yes, but the cool thing is I think Nick found a website that's an entire book about building expert systems, and not like expert, but like you train them, and so you kind of give them all, like I think it was like bird.
Yeah, the example was bird identification, and you specify rules that this bird has these qualities, this other bird has these qualities, and then you can abstract some of those out to say that waterfowl have webbed feet, and
Feathers.
No,
Yes,
that's about
feathers.
that's about keys, right? Like
Yeah.
it's this the goose.
Yeah, so for example, you could write two rules for determining if it's a Canadian goose based on when and where it was seen, and you could say that it's a goose if it was seen in Canada during the summer. It can also be a goose if it was seen in the U.S. during the winter. So, and it'll try all those different rules until it can find one that can unify and provide a valid response.
And at
So-
the very end, when instead of saying yes, it says what's good for the goose is good for the gander. Anyway, weaknesses. Utility, obviously, it's a very focused niche logic programming, like you were saying. Focus. This is and it doesn't do well with very large data sets, you know, and so yeah. Thanks.
Are we doing day 3?
This we pretty much covered day 3 with this example.
Okay, cool.
So,
So moving on to what's the next chapter?
Is it Scala or Scala? I don't know.
For scalability.
It's
Scala.
Scala.
Scala?
Scala.
Everybody.
Scala.
I don't know.
In Brazil, Scala.
That's
In
Scala.
Brazil.
In Brazil, it's Scala. So
Scala.
Scala.
Alright, so in Brazil,
Compared to
so we're
you.
gonna call it Scala.
They're trying to distance
So we're done?
themselves from the whole
Sure.
scaling thing.
Bye.
Alright, bye.
So they changed their name?
No, that's not true.